No, I'm here. I'm just trying something out. I was trying to um have everything broadcast live on YouTube. Okay, so now we're going to be broadcasting live on YouTube. It's going to be a bit time delayed. So people are going to be watching this later. And hopefully it'll record the stream.
Is this permanently going to be on YouTube?
Yeah, but I'm going to make it unlisted. So, like, people won't be able to find it. Unless I give you the link.
Sounds good.
It seems like a more permanent solution for this. Oh, that's unnerving. I'm going to have to hide that from myself. Looking at myself with a time delay is so weird. At least when I have like this on Zoom, at least it's somewhat not on a time delay. But having more is like, oh no. Nope, can't do it. Okay. It seems to be like a more permanent solution that I'll have to do, and I'll label them afterward, like which class it refers to. I'm just trying it out, see how it goes. If it doesn't work, I'll just keep what I'm doing, because oh, now we're recording. Okay, so I am trying something new today. I am trying to broadcast live on YouTube, and hopefully it'll record it, so we will like have that saved for time, because I'm getting some messages that hey, we're using up all of our space on Confer Zoom. So if you could like limit your ones and maybe delete videos you don't need anymore, that would be great. Thanks. Bye. Anyway, so I'm trying to figure out a way like have a more permanent solution so you could see everything on that. Yes, Jenna.
So the new recordings are not going to be available on Com for now. It's just going to be on YouTube.
I'm going to do both for now.
Okay.
Both for now. See how they work. Because I'm preparing them to say, hey, Professor Roberts, you're taking up too much space. Delete some. So I'm anticipating that. So for now, they'll both be up there. It's going to be transition. We're trying things out. Because we did not expect the pandemic to last so long. Other questions? All right. There's another short little TikTok I want to show you guys about learning.
People will ask me on.
Wait.
Hello, here's a werewolf. People.
All right, try this again. So, share my screen. It's my phone. This is something I'll incorporate in the future. Oops, I need to share my sound though. Otherwise, you won't hear a dang thing.
This app fairly frequently. How do you know so much?
Try this again.
People will ask me on this app fairly frequently. How do you know so much stuff, man? Well, there's a lot to that. I've been doing this kind of work for a long time, so some of the information I come across actually sticks. But the biggest tip I would give if you are actually interested in having a more robust understanding of the world is to like notice when you get curious about something and don't let it go. Hold on to it. If you have a question that you want the answer to and you don't know the answer to it, ask that question, maybe even write it down and try and figure out the answer. It might be a research thing. It might be just internal. It might be just thinking about it for a long time. But trying to figure out the answer to a question you do not know the answer to is how you build knowledge. And like a lot of knowledge building in like sort of formalized education is that without the question first. It's like, here's the answer, but I never asked the question. Ask the question. People will ask me on.
So, Yeah. That's what I hope you guys think about knowledge. Asking questions. And so I have of the philosophy, there's no bad questions. Well, that's a little concerning. Why does it think it's 9:40 in the morning for my phone? That's bad news. I'll have to figure out what's going on there. Oh, that's weird. That's doubly weird. It only thought that while it was connected to my computer. And my computer doesn't think it's like that time either. So weird. That's normal? For the time to get weird on it? Huh. Alright. As long as my phone just actually knows what time it is, and not that weird time. Alright. You'll see, like, my iPad knows what time it is. Oh, before we do that, though, I want to show you some stuff on how to use Desmos. Desmos. Go away. Go. Okay, just was logging in. Let's share my screen. All right, so I recommend if you don't have a Desmos one, just go ahead and create a Desmos, and you can actually have a whole bunch of graphing functions here. The reason why I'm recommending this is because you can save things, unlike on Wolfram Alpha, where like, pay us first. They're like, it ain't free. It's great for doing units, but like probably in terms of long term, you may want to get a Desmos account. What's all these things here? Okay, tours. Okay, so you have a whole bunch of tours that you can do, and blah, blah, blah. But let's go ahead and jump to the part what's relevant for you: regression. So let's go ahead and go through the tour. Sample data. So we're going to copy and paste the sample data. Copy. We're going to paste the sample data right here. Paste it. Paste it. There we go. Add a new item. We're going to add an expression. Now we're going to type y subscript. So you do subscript, you do, oh, to get y1, just do y1. Okay, like that. And then you do tilde. And then you do mx1 plus b. And there we go. There's a regression plot. It has some good parameters here. And there's the error in all these data points. And you can see the error. So when you're doing any regression plot, if you have a trend in the errors here, probably something went wrong. This is how you analyze your data. Do you see how there's a trend in the errors? See, it was like below, then above, then below again? That probably tells you that a linear fit is not the best fit here. So that's why they're saying, hey, maybe let's try another model. Maybe a model that might be better is quadratic. Let's try it. So we're going to do A parentheses x minus h plus b. And look right there. Oops. I was not trying to end that. Let's hit the back button. Leave. Go back. Let's try this thing again. So let me get through it again real quick. Regressions, sample data. Okay, let's copy this back again. Paste it in. So I'm just going to go through it quickly. Whoops. Paste, expression. Okay, go through this again. So you can do this with your data, by the way, and just take screenshots of it. So there's the regressions. Okay, let's add another fit. Expression y goes as a x1 plus or minus h squared. So we do squared plus b. So see, these follow it a lot better. See how the green residuals are actually pretty, you can zoom in on them. See, they match them almost entirely better. And that shows you how to do different regressions. And that's how you can, if it's easier, you could probably do it here rather than either. So you have one of two options. Either you can have the model do it for you, or you can have it do it like that times squared for the lab. Do you guys have any questions? Ew, stop flying around. Any questions about those Desmos things?
This is specifically for the lab data, right?
What was that again, Victor?
This is specifically to graph the lab data.
Yeah. So you can do regression in Excel, or this might be helpful too. I think Desmos probably might be easier, more straightforward, but just make sure you have the error though, because that's why when you're doing your analysis, you should note. You'll probably see that there's going to be an error that has a trend here, so that means it's not the best fit. Yeah, stop it. It's not the best fit, since there's a trend to the error. And that's why we switched to the curve. Okay.
Once we have the data as a group, we individually do our graphs.
Well, you can work as a group too.
Okay.
What's the tilde?
Tilde, if you're on your computer, it's the one. If you do shift, the one the.
Oh no, I mean, what's it stand for in the expression?
Oh, goes as.
Oh, okay.
And I guess Desmos recognizes as fit a regression line to that. I don't know all the Desmos stuff, but that's what I think Desmos is reading as. Make a regression line of it. See functions here. Stats. Oh, we can do other things here too. So many things. You know, a whole bunch of visualizations. Oh, so many cool things. I'm gonna have to learn some things. All right, that's gonna be my project. I'm gonna do this weekend. I'm gonna play around with Desmos. There are so many things that we can do, and it's free. That's what's great. After the break, I'm gonna go ahead and give. I'm gonna try and have some data, and we're gonna play. I'm gonna show you how we can do regressions on that. Okay, but while I do that, let me get some water. It's a very powerful free tool is all I'm saying. Just giving you more resources to use. You could use Excel, or I think even like Google Docs can do it too, or Google Sheets can do it as well. This does it all for you. And yeah. So you can also make the parameters better by doing this stuff right here with nonlinear stuff. So if you do a nice linear one, so it's like, by the way, linear here means in the context of like, see right here, like a polynomial, because it's a linear combination of A, B, and C. This is a nonlinear one here. So here, this is well, I guess you can still make this linear here, but like you can make it explicitly like a linear regression by squaring x instead. Like if I take a column, like squaring x, take a column where I square y. Anyway, we'll play around with that after the break. Let's stop the share. Make it to your thing. Physics 21, chapter 3. Okay, this is where we left off. Excuse me. All right. So we're going to move on to talking about motion in a circle. Yep. And then we're going to talk about relative velocity is the other thing we're going to do. So let's define some coordinate systems. All right. So here's a circle here. And let's consider moving around on that circle. Let's define some define coordinates that are more relevant for motion in a circle. So this is your Cartesian coordinates here, x and y. Let's define coordinates. Or let's define polar coordinates. For motion in a circle. So we still have an origin, as all good, superhero stories have. And except instead of having X and Y coordinates, we're going to have what's called R and theta coordinates. So let's make point P out here. Beep, 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 point P. So we could have this as, let me do this in these colors here. X and Y. Not these colors. Let's do different colors. Let's do these ones. No. Yeah, let's do these. X and Y. X is going to be this way, X hat. And Y hat will be going this way. It looks like I got to get that point P out of the way. All right. All right, so far so samey, right? Oh, yeah. You already this is all old hat now, right? You guys are all bored. But let's go ahead and add a little bit to it. Because X will be the distance from here. This is your X coordinate. And this here was your Y. But how about instead we make a new coordinate called R. The distance from your origin. Call this R. And let's call this angle here theta. Right? With me so far? So we always measure here. R is let me write this out. R is the distance to the origin. And theta is the angle the radius R makes with the positive x-axis. So this will be theta equals 0 right here. All right. So what if I wanted to say, well, what direction do the unit vectors for these coordinates point in? Well, R is going to point in the direction of increasing R. R hat will be increasing R. So let's have that pointing in the same direction here. Make it new colors. So red. So R hat is going to point this way. And theta hat is going to point in the direction of increasing theta. Which is outward. Negative will be inward. And theta hat points in the direction of increasing theta. So this is positive is counterclockwise. And negative is clockwise. All right. So what if we didn't have this point right here? What if we had this point right here instead? While x and y are still in the same, x hat and y hat are still in the same direction. R hat now points in the direction of increasing r, which is here. And theta hat points in the increasing theta, which is going to be this way. Bit of a brain bender, right? But does it make sense, though? Or at least you following so far?
So, sorry, the one near the Y at the top right, that's counterclockwise?
Well,
That
these are
one's
both
negative?
they're both counterclockwise
Oh,
around this origin. Good question. Other questions?
okay. So they're both negative and the same thing for the arc, correct? Is that
Wait,
when,
what? Wait, what? What do you mean they're both negative?
so like the counterclockwise for the theta hat, that one is negative? I mean positive?
This is the positive direction for theta, yes.
Yeah.
You can keep on going around the circle. It's the right-hand rule. Put your thumb on the origin, point towards you. Your right hand curls in positive theta. Let's do one here. And another one right here. I'm going to not have the X and Y hats because they're, the same. And just draw the R and theta ones. So that's R. And R hat's going to be increasing. R hat and theta hat. No, don't snap to it. Technically, they're all supposed to be length 1 here, but that's kind of hard to draw. So then here is R hat is going to be increasing R. And theta hat is going to be perpendicular to it. And these are all supposed to be the same length. They're all length 1. I just wasn't consistent. Questions? So the unit vectors are all length 1. And here, they're perpendicular to each other. By the way, you don't have to have unit vectors to be perpendicular to each other, just not parallel to each other. But usually you define perpendicular unit vectors. Okay. They're all at right angles to each other. Just like how your Cartesian ones are. By the way, if you do in 3D and you use spherical and cylindrical coordinates, the way we define them is slightly different in physics and math, so just be aware of that. This applies for both motion in a circle and motion, or any motion. It's just in a circle, since r is constant, it's more convenient to have this instead of x and y, because r will be constant. These coordinates can be used on any trajectory. So kind of like how we had like parallel and perpendicular components of a velocity, this leads into radial and tangential parts of acceleration. With me so far? Or any questions so far? Oh, my back just popped. All right, so now that we have all the terminology now, let's go ahead and talk about defining things. Particularly, I want you to remember that outwards positive and inwards negative, because that's going to how we define our acceleration when we're going around a circle. So if we have uniform circular motion, it's a special kind of motion. It's constant speed along a circular path. It's a special one we use. By the way, the acceleration that you experience A is going to be, if this is your velocity here, it's always going to be tangential to your circular path. So your acceleration is going to equal v tangential squared divided by r, and it's going to be inward, so it's going to be in the negative r half direction. Because it's inward. We do it in R. R. One more time. R. This, by the way, is called your radial acceleration. And the acceleration needed to keep on a circular path to exactly stay is also known as the centripetal acceleration. The force needed to create this acceleration is called the centripetal force. Well, although I like to think of it as more as the force in the centripetal direction, because it's more toward the circle. Although, for my taste personally, I'll tend to use radial because it's more general and more exact. Centripetal leads into, because usually you guys are used to saying, oh, there's not like an X force and a Y force. But a lot of the time, people are used to saying, oh, there's the centripetal force, as though it's its own thing, which it's not. Centripetal force is just the force in the centripetal direction. Okay? Questions? Let me write down what I just said out loud. Diagrams. We haven't done force diagrams yet, but I just wanted to have that ready for you guys. About that already. Questions about this so far? So we're going to call this, actually, we're going to call this radial acceleration here. Is a word phrase I'll use more often. Okay, I can't tell whether your silence is like, I don't get it, silence, I'm writing things down, or silence, I'm bored. Can I have a check-in with everybody? Writing, okay. Copy notes, all right. Fair enough. All right, well, we'll get to that in a bit. What about centrifugal force? Oh, good question. Let me have everyone catch up and then we'll talk about that. Since we're talking about this already, we might as well. I mean, so we haven't really introduced forces yet, but we might as well talk about it right now. Raise your hand if you need more time. And we'll define centrifugal and why that I will almost never use it. Screen is blue. Oh, there you go. How about now? Back? Are we back in business? Yep. It ain't perfect. I'm getting vaccinated tomorrow, so they're like the timeline on this. It's like I've been hearing anywhere between like, oh, maybe end of May to December. And so when I hear like Mississippi and Texas saying we're going to reopen, I'm like, no. Yeah. That's what I was thinking. I mean, I understand that they're going to do that and it's really hard. because of capitalism. Because it's, if we were safe, we would want like to snuff it out for the workers. But we're a capitalist system. We gotta let like the only way that you can get your work, get paid, is if you work, and so you have to go to pay the person to work, and so they're gonna reopen this then, and it's gonna keep the coronavirus alive rather than like valuing the people. We value the work. I can go on anyway. I'm not gonna go on a rant. Yeah, awesome. That's great. But yeah, I'm not going to, of course, to pretend like there's not a division between, like, science and politics. Anytime there's people, there's going to be politics. And so I'm not going to, like, pretend like it's not there or be frustrated when those kind of things happen. And where it comes from. It comes from capitalism. I've got some thoughts about that, which you probably have intuited already.
I'm not sure if you said this, but I just wanted to re-clarify. Did you say that the velocity is changing when in the circle?
Oh, so I should clarify. The constant speed. So the velocity is changing because it's going around in a circle, but the speed is not.
Okay, so it's like constant speed, different velocity. And does that include the acceleration or?
Yes, this is the acceleration. If you're on a circle, where the acceleration's, if you're on a uniform circular motion, this is a special case. Uniform circular motion should be in your vocabulary. If you see uniform circular motion, you can make these assumptions. 1, it's a constant speed. 2, it's a circular path.
Got it. Thank you.
Yeah. Now, and 3, this is your acceleration. So let me write that down. 1, whoop, go away. 1, constant speed. 2, circular path. 3, this is your acceleration. All right. Raise your hand if you need more time. Yep. All right. I'm going to do a little stretch. Have your hand raised so I can... yeah. All right. I'm going to do a little stretch break. Okay, any other questions before I talk about the centrifugal force? Ft represents the tangential velocity. Is the velocity tangent to the circle. To the circle. As I said on the previous slide, you may have systems where you're not going on a circle, like if you're spiraling in or you're spiraling outward, while the path will always be tangent. So you always have the velocity tangent to the path, but you might not necessarily have it tangent to a circle. We're not going to explore that too much right now. We're going to return to it. I refrained from saying circle again. We're going to return back to this idea when we discuss motion, like dynamics of rotational motion later. So that's why we have V tangent, because while will always be tangent to the path in blue, it won't necessarily be tangent to the circle, which is why we define the tangent. Okay, other questions? All right. Give me. Okay. So, is it going away, or you guys can still see it? Did it disappear?
We can still see your notes.
Okay, good. All right. So the centrifugal force it is a inertial force sometimes called a fictitious force.
Are you writing stuff down, Professor? We can't see what you're writing.
Okay. There. How about now?
Yeah, that's better.
That appears to act on all objects when in a rotating frame of reference. So inertial, meaning that an object will want to stay in a constant velocity. So it's not that the object's getting pushed around, it's that you're pushing around the whole system and it's trying to stay in the same spot. And so relative to you, it looks like the object's moving. So it kind of looks like all objects kind of get splayed to the outside when you have a rotating camera. Which is how a centrifuge works. It's not that the centrifuge is actually, pushing out on it. What's actually happening is it's pushing it inward the entire time. And it feels that force. It only looks like it's being pushed outward from our reference frame, which tracks the motion of the centrifuge. So usually we just have our eyes will track what's the simplest motion. There's actually a really good video about frames of reference. We don't really have time to show it in class. But I can give it to you so you can watch it on your own time. Which I highly recommend. It'll answer lots of questions. But let's go ahead and see some examples. So see this one right here? So this appeared to get pushed outside here, but actually it tried to go in a straight line. And you got a whole bunch of things right here. So like if you spin some water, like a spin a bucket, it looks like the water gets pushed to the outside. What's actually happening is that you're pushing the water inward, and it's gonna, look like it's being pushed to the outside. This is actually what it looks like. We'll come back to what all these things later are, but that's what it is. Boop, 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 boop. Back to here. All right. Good question. Other questions? Let's talk about motion in a circle when you don't have constant velocity. So if you have velocity that is a car that's speeding up, going in a circle, you're going to have an acceleration that's tangent to it. So I'm going to call that, you can call this, this will be like your radial acceleration here. A sub r. And this would be your A sub theta here. The acceleration that's rotational. Okay. And note how the acceleration is a little ahead of the normal here, where this is the normal here, toward the center of the circle. Toward the center of the circle. Okay. And if it's slowing down, if you're hitting the brakes on a circle, you'll have this acceleration a little bit behind. And this is your radial acceleration. And this is your theta acceleration there. And, just like before, you could write it as a x hat plus a y hat. You could just as easily write it as a r hat plus a theta hat. I definitely can. Cool. Boop, boop.
Just to say real quick, the A theta, our acceleration degree, would that be like something that would be the degree comparing our v vector to our A vector?
Right. So A theta here is it's related to, but slightly different. It won't be measured in angles. It'll actually be still be meters per second squared. There's something else that we're going to called angular acceleration, which is, a couple chapters away. But that will be the angle version of that. This one still has units of meters per second squared.
Got it. Thank you.
There will be a simple conversion between those two later. This is also sometimes known as tangential. So you can also let this be called... Wait, which one again? Nope. Not this layer. We're here. This is also... So aka A sub t for tangential acceleration. Mean the same thing. I just want to have it be the coordinate be the same. All right. And yep. Okay. Any questions? So let's take a 10-minute break, and then we're going to come back, and we're going to derive that expression that I gave you. V squared over R. Sound good, right? So excited. So excited. I know. Can barely wait. Let's take a 10-minute break, though. Yeah. So let's do it at 5 o'clock. See you guys in 10. Okay, so we're back. On William's note about being back in person and not online, probably if we do come back online in fall, it'll probably be in staged version, particularly if you have any symptoms like that. So hopefully, if you're sick, you're not forced to come into class. You can watch it later. It also will be like if schedules get weird, that the standard will be it's recorded for you guys to watch later too. Well, because, yeah, we should just have like, I mean, the flu was just snuffed out basically. Even though I did get my flu shot too, there was like very little catching the flu because everyone wore a mask and everyone's social distancing. That's like, yay, no flu. And personally, I'm gonna keep on doing this where I draw on, diagrams from a textbook because then I can do my own little stuff on there. Woo! Speaking of which, let's consider so we're going to derive the expression
Professor, we can't see your screen.
oh, of course. Oh, right, I need to share. Thank you for reminding me. A r equals negative v tangential squared over r. Okay, so let's first consider uniform circular motion. Okay, so that means constant velocity and it's on a circle. Constant speed, sorry. Constant speed, magnitude of velocity, and constant r. So let's take 2 points right here. Point 1 right here and point 2 right here. Each with having a velocity v1 and v2, where the magnitude of v1 equals the magnitude of v2. Okay, and let's say this takes a certain amount of delta t.
Professor, does that say first let's take uniform circular motion?
First consider uniform circular motion. Consider. Let's say a particle moves from P1 to P2. In time delta t. Okay. And there is a displacement delta s. Technically, if you zoom in right here, you'll see that it's actually not the arc length right here. It's the actual displacement. Actually, no, sorry. With distance. Displacement. Delta S. Although that's not going to be important when we take the limit, though. All right. So that means the angle between these two that's going to change is going to be delta phi here. Angle, the radius makes with the center of the circle changes delta phi. Excuse me. Excuse me. By the way, so if I shift V2 to be at the tail of V1, you get this triangle right here. And you can prove these two triangles are similar. Let's show you how. So we have this one right here. So this is a right angle to this one right here. Well, it's not, these aren't right angles yet. So if we have this be a right angle right here, let me do it. Oh, come back. Stop it. So if you extend this line out here, this is a right angle right here. And extend this one out. You get a right angle right here. Because it's tangent to the curves. So we can, if this is, if we move this right here to here, let's see. So you can see this triangle right here, this one right here. Hold on. How can I do this? So you can, like, when you move this one right, when you translate this one down to here, you can see this little angle right here is the same one as, well, let's see. This is the angle right here. And we're going to translate this down right here. So this one, if we had like this, so we had V1 and V2. With a delta phi right here. This right here, this one was V2 right here. And this is V1. So this is a right angle right here. So when you translate V2 to here, this is going to be delta phi, because this is now still a right angle here. Because these are alternate interior angles. And this forms a right angle right here. So since this, so when we transpose this right here, V2, down to here, it's going to split this right angle right here into some angle here and some angle here. We know that this is perpendicular to the circle because we know that V2 is perpendicular to the circle. And so it's perpendicular to this radius right here. So this is a right angle here. So on the opposite side, extending it out, this will also be a right angle. Yeah? So when I translate this down here to here, it's going to split this angle. So this is a right angle. This is theta, or delta phi. And this one's going to be 90 minus delta phi for this angle here. So then this has to be delta phi. Sorry if I took a little second there. I got a little confused with my notes. But hopefully did I caught you guys up to here?
It basically splits into two triangles.
Yeah. So
Okay.
like I drew this one out for V1 all the way through. So here's V1 right here. And here's V2 before you translate it. So this right here, this is at a right angle here. This is the line connecting P1 to P2 directly across. This is P1 here. And this is P2 right here. So P2, at P2, there's vector V2 that comes straight off at a right angle versus the radius here. So this is a right angle here. And you have vector V1 at P1 that's at a right angle with a radius here. Hence this right angle I drew here. So now I'm going to move V2 to here. To have the tail to tail here. And I wanted to find this angle right here. Well, you can see that it actually splits this bigger right triangle right here into two parts. So you actually have, three similar triangles. You have this one, this big massive one, this one, and this one. They're all similar triangles. And this one, the small one, is the one right here.
Professor, what's after the delta on the far right, what's the symbol next to it?
This one here?
No, far right. Yeah.
That's a phi as well.
Okay.
Okay. Let me go ahead and hide that. All right. So now we've gotten to the point where this is our triangle right here. So that means that since these two triangles are similar, that means that we can say that this to this is the same thing as one of these sides here to none of these sides here. So, since, oops. That means delta S over R equals delta V over V1. Or, to rearrange it, magnitude of this right here. And then solving for delta V, it's going to be V1 over R delta S. Raise your hand if you need more time on this. I'm actually going to... okay. So what we're going to do next is we're going to find the average acceleration. Because this is a change in velocity, if we divide by time, it'd be because we say it's going to happen in delta t, we'll find the average acceleration. magnitude of average velocity divided by delta t. And that's going to equal v1 over r delta s over delta t. If we want the instantaneous acceleration, we take the limit. So in the limit, delta s is the distance the particle moves along the curved path because it's so short. Or just, v1. Equals v1. And so acceleration equals v1 over r times v1, or v1 squared over r. Or, to remind us, it's the radial acceleration. And it's going to actually be negative because it's going inward. Okay.
The acceleration of r is inward, right? AR?
Yep.
Okay.
So centripetal acceleration, by the way, means seeking the center. So if you have uniform circular motion, here's what it looks like, versus projectile motion. And you can see why we chose different coordinate systems for them. Raise your hand if you need more time. All right. So here, if you have uniform circular motion, the acceleration is inward. It's constant magnitude but varying direction. And projectile motion has constant in magnitude and direction. Which is why we use Cartesian coordinates here and radial coordinates for this one. Or, sorry, polar coordinates here. Sure, I'd agree. That would be a pretty good idea. By the way, you could talk about the period of how long it takes to go around. Well, so what's the period of circular motion? Because the period is how long it takes to get to where you started. We're going to come back to this when we talk about periodic motion. So the period in physics and astronomy So this is actually, in our sense, will be one for us for this in this case. One trip around the circle. But you can also talk about the orbital period of, say, the Earth around the Sun, or the rotational period of the Earth around its axis, the orbital period of the Moon. We'll come back to this. There's many different things. It is, yeah, well, it is from the textbook, yes, but it's a good diagram to have down. Okay. So it's going to be the circumference divided by what I'm going to call big T. So the circumference of a circle is going to be how fast it's going, right? The distance over time, right? So what's the circumference of a circle? Yep. That's supposed to be pi, yeah? Yeah. Two pi r divided by the period equals the velocity. Or, to write in a different way, the period equals 2 pi r divided by v. So to plug, if you plug this into your acceleration, it's going to be the radial acceleration equals minus 2 pi r, sorry, 4 pi squared r divided by t squared. Because this is why. R equals negative vt squared over r. So we have negative 1 over r. So it'd be 2 pi r squared over t. And so one of the r's cancels, and this becomes 4 pi squared t squared. So you get this. Boop, boop, boop. All right. Questions? All right, let's go ahead and do a practice problem. So an Aston Martin V12 sports car has a lateral acceleration of 9.97 g, or 9.7 times the acceleration due to gravity on Earth. This is the maximum centripetal acceleration the car can sustain without skidding out of a curved path. If the car is traveling at a constant 40 meters per second on level ground, what is the radius r of the tightest unbanked curve it can negotiate? Sure, I definitely can. So, this one we are given, what are we given? Acceleration, and we're given r, and we're given tangential velocity. Let's draw a diagram. Alright. Fill vector. By the way, when you're doing centripetal motion, generally we'll have two different types of diagrams: a top view and a side view. We're going to consider the top view first. So our velocity is tangent to it. And our acceleration will be perpendicular to it because it's a circular path. So it's going to be... So we have a radial acceleration here. So this one is V tangent. So the V tangent is 40 meters per second. And your radial acceleration is 9.5 meters per second squared. And we want to find what's the radius here. Okay. Okay, questions so far about the setup? You always want to do a diagram so you can get like a view of this. Because isn't this already like things coming into focus more than just the words here?
Yeah.
Okay. So we're going to... Cool. Definitely. Awesome. We're going to use the expression AR equals negative V tangential squared over R. Here it doesn't really matter what direction it's going in. So we're going to just solve for the magnitude. So R is going to equal V tangential squared divided by the magnitude of AR. And we have 40 meters per second squared divided by 9.5 meters per second squared. And when you crunch those numbers, you get 170 meters. Rounded to 2 digits. Or about 560 feet. Pretty tight turning radius. Nope, I put the absolute value sign here. Didn't need it.
I just want to make sure R is the magnitude because that's the entire distance the car traveled.
Sorry, what?
The reason R is the equal to the magnitude is that due to
Here, hold on. Let's just, you know what? That's actually, I think, tripping a couple people up. Let's do this. So actually, AR here is going to be negative. Let's just do it. All right. I think just, yeah. Because it's inward. So now it'll be the negative of negative, so it's going to cancel. There we go. Now it'll work. Because it's inward. The car is turning inward. Inward. Fair enough. Both you guys are like, no, don't keep it consistent. There, now it's consistent. Fair enough. I won't be sloppy. Other questions? Sure. Yeah. It won't change the answer really. Jason, yeah. Other questions? All right, let's do another problem. Passengers on a carnival ride move at a constant speed in a horizontal circle of radius 5 meters and making a complete circle in 4 seconds. What is their acceleration? Let's do another diagram. Oop. Let's draw my circle. Let's go ahead and fill it in with a vector and then shrink it down a little bit and then put it back in the center. Okay. All right. So let's have our passengers here. I think this is like the gravitron. You know, the ones like a blurp, push against the wall. You guys ever experienced the gravitron? No? Oh. It's I guess if you haven't been to like a carnival, because they don't really have it at theme parks. It's like at, fairs and carnivals. And it's like, depending on how good the theme park is, it can be, of varying levels of safety, depending on how much the ride operator is really paying attention to say, no, don't stand on the this right here. But this spins fast enough, you can create enough G-force to kind of make your up feel different. So, we have the radius though. Whoops. I'm going to have this go counterclockwise because it just makes it easier for me. They don't tell you it. They just tell you that it has a radius of 5. And they tell you the period is 4 seconds. That's pretty fast. And by the way, this is pretty much the only way you're going to get gravity in space, is by spinning people around in circles. There's no such thing as gravity plating. There's not going to be... Yeah. So... The only other way you could do it is using what the Expanse does and have constant linear acceleration. Although, to have something that creates 1g of acceleration in a certain direction, well, if you know what can do that, let the rest of the scientific community know. Don't hold out on us. We don't know anything that does that. So probably the thing that we'll use to create gravity is spinning things. Spin round the go. Okay. So they're asking for what's the acceleration. So the acceleration inward is going to be minus. So they're giving us, instead of velocity, they're giving us period. So we should use 4 pi r over t squared. Oh, it's negative, by the way. Negative 4 pi squared r, which is 5 meters, divided by 4 seconds squared. And you get negative 12 meters per second squared, because it's inward. Or negative 1.3 Gs. So that's, quite a punch. You would definitely feel even a little heavier if this was in outer space. Well, presumably if it had all the oxygen still inside it. If this was in outer space, you would feel quite a bit heavier than you would on Earth. So, I think they actually have, the inflatable space hotels that they're going to put people in, because long-term exposure without gravity can cause some problems, because our bodies evolved to live under 1g of acceleration. Everything will start going weird. Your heart will pump a little strangely. It'll get weaker because your body's like, oh, we don't need anything this bone density or muscle mass. Dump it all out. And so you lose bone mass density and muscle mass, because your body evolved to be we're going to be a lean fighting machine. So anything you don't need, toss it. So there's like right now what astronauts do is they have like weird resistance training where they basically have like little rubber bands where they have like weights with rubber bands on them that you have to resist against. If it's in gravity, you wouldn't have to do that as much to keep your bone density and muscle mass up. By the way, some roller coasters, the ones that go like loop-de-doops, you can get, G-forces as much as 4G.
Wouldn't that be negative 5 pi over 4?
What?
The answer, wouldn't it be negative?
Oops, forgot squared there. Oops. Thank you for catching that.
Mm-hmm.
Thanks, Luca.
But wouldn't it also be 5 over 4, which would be...
Wait, what? I don't see it be 5 over 4.
Because you square the 4, and then it'd be negative 4 pi over 16, so the 4 would cancel to 1 and a 4 on the bottom, 5 over 4, pi squared.
Wait, well, let's do it out. So it's going to be negative pi squared, so it's negative 5 pi squared over 4 meters per second squared, yeah?
Yeah.
So pi is about 3, so that'll be about 9 times 5. 9 times 5 is... no, that makes sense. Like 9 times 5... So this is about 9 here.
Yeah, never mind. That makes sense.
Yeah. Yeah. Don't forget about the pi. I forgot about a pi. Other questions? Oh, negative 5 pi squared over 4 is 12. More exactly, it's 12.3, more exactly. By the way, let's go ahead and go over a couple of ways things go wrong when you're talking about circular motion. I'm going to steal this from your textbook because I think it's important to go over. Anytime it says something like data speaks in your textbook, oh, look at it because it's probably, useful information. So when students were given a problem about an object on a curved path, not necessarily of a parabolic path or of a projectile, more than 46% gave an incorrect answer. Here are some common errors. Confusion about the acceleration vector A and the velocity vector V. Remember, A is the rate of change of V, and on a curved path, A and V cannot be in the same direction. And the confusion about the direction of A vector. If the path is curved, A vector always has a component toward the inside of the curve. So always note those when you see something like that. All right. Are you guys ready to talk about non-uniform circular motion? All right, let's get to that. So if the speed varies as it goes around the circle, this means that velocity is no longer constant. So we still have the radial acceleration is still going to be negative v tangential squared over r, except now it's going to change as v tangential changes. So then there's also going to be a tangential component, which I'm going to call a sub t or a sub theta. And it's going to be the derivative of the magnitude of the velocity with respect to time. Because this this vector, right, this one right here is changing the direction of the vector, and this one, or not. And since we are going in a circle, it's completely changing the vector, going in a circle. This is the changing the direction of the vector. This one is changing the speed of the vector. Changes the direction of the vector. And this changes the length of the vector, of the velocity vector. A little note right here for this right here. If AR is more negative than this right here, then it spirals inward. If it's less negative, it's going to spiral outward. It's like too much change of that or too little. We're not going to consider these cases right now because we're on a circle still. So it's going to be exactly this. And this happens a lot. Like, let's say you're swinging a bucket in a circle. Like this. Like, usually, unless you're very careful, you're not going to have it go exactly all the way through at a constant velocity. I can actually feel it. It's actually a lot harder to do than just let it go like that. Because most things that are swung in a circle are not going to have uniform circular motion. At least it's that way. On a table like this, yeah, you can get uniform circular motion pretty easily. But ones in a vertical circle, or where part of the circle is in the vertical direction, it's hard to get uniform circular motion, so it's non-uniform. Like a roller coaster, for example.
So uniform circular motion is like a perfect circular motion, and non-uniform is like jumping up and down, spiraling everywhere, something like that.
Well, I mean, this is like even different from this right here. I just wanted to let you know, like, oh, like, there's even more non-uniform motion. This would not be circular motion at all. This right here, this is in black here is for non-uniform circular motion. Non-uniform circular motion is this in black. This is for motion that's not on a circle. Say an ellipse. Because that's a shape that'll come up later when we talk about orbits. But back to here, that this is common. When the circle is vertical. Try swinging your arm in a circle. Like this. It's hard to have it go in a uniform circular motion. It'll be non-uniform because it'll be easier going down than back up. Okay, did that help clarify that? Okay, it's reminding me flex days tomorrow. Did that help clarify that, Victor?
Yeah, a little bit. Thank you.
Okay.
I'll probably read a little.
Okay. Yeah. So this is the case for of course you should read the textbook too. None of this stuff really that I'm saying makes sense unless you're following along in the textbook. Raise your hand if you need more time on this. We're not going to have enough time to cover what are we talking about? Oh, relative velocity. So we'll do that on Tuesday. All right. So, important to note is that for non-uniform acceleration, circular motion, I mean, non-uniform circular motion, here's two quantities. D.
Professor, we can't see the screen.
Really? No one can?
I meant the new screen. You're showing the.
No, we can't see what you're writing right now.
Yeah, that.
How about now?
Still
We
no.
can't.
How strange. Let's try again. Thank you for letting me know. How about now?
Complete black. Black screen.
Okay.
There you go. Perfect. All clear.
Cool. Thank you.
Perfect.
Thanks. All right. So, for non-uniform circular motion, the derivative of the speed or magnitude of velocity over t does not equal the magnitude of the derivative of this. These are not the same. This is the tangential acceleration. Or acceleration going around. This is going to be the magnitude of acceleration. So, magnitude of the derivative of the velocity with respect to time is going to be the square root of the radial plus the theta squared, square rooted. So this will only be 0 if the particle's acceleration is 0. Right? So here's an example of your textbook. I want to copy it down. So here we go. Here's what non-uniform will look like here. Like on a roller coaster. E.g., a roller coaster, or a bucket swung in a circle. So here you have the acceleration will be inward, and then it's like slowing down as it goes up until it reaches the top, and then it starts speeding up again. Because you'll have something that's accelerating inward the entire time, and then part of it like that slows it down going up this way, like gravity, and parts is going to speed it up again like this, gravity again. Okay. So I'm looking at. I only have a little bit of time left. Let's go ahead and just start a little bit relative velocity, and then I'll, talk about it more on Tuesday. Sound good? Raise your hand if you need more time. All right.
What does the example say, Professor?
This right here.
Yeah.
Non-uniform circular motion, like a roller coaster or a bucket swung in a vertical circle.
Okay, thank you.
Okay, moving on to our last topic, relative velocity. And we won't be able to finish it. We'll kind of just end where we end. Relative velocity. So I kind of already alluded to this, like with the inertial, but let's talk about relative velocity. So we can always reference our own velocity to our own frame of reference. So a frame of reference is a coordinate system. And a time scale. So basically like a meter stick, you can hold in different directions, and a stopwatch. So until you get to relativity, special relativity with Einstein, we're going to use Galilean relativity. Converts between two frames of reference.
Professor, what does it say before relativity?
Galilean.
Got it.
Galilean. Two frames of reference. At different speeds, references, frames of reference that have a relative velocity, a by, and here's an example from your textbook where you have like a cyclist and a passenger on a train. And here's what it looks like when you do it out. So we have x. So this is going to be P's position from A's frame of reference is going to equal the position of the cyclist or passenger reference to the train, which is B, plus the position of the train relative to the cyclist. So you can kind of see how this kind of condenses away right here. By the way, I'm using position coordinates. Time coordinates behave the same way too. And derivative is just applied directly. So we have velocity of P A in the x direction equals velocity of P from B in x direction plus V of B, A in the x direction. And as you can see with this little subscript right here, you can already see that it's going to be converted into 3D like this. All right. So this is the conversion right here. You have to make sure you have this order matters here. The order of these matter. So this is position of P from A's position, from A's perspective. So this is like the objects you're observing, and this is the observer perspective. And these are the frame of reference, which I'm going to just abbreviate as FOR. FOR. Because I'm going to write that phrase a lot, frame of reference. Okay? One more thing is that if you flip those around, the velocity of A with respect to B isn't equal to negative of velocity of B with respect to A. So let's say that this is... So I hope you guys all watch this video I'm going to post about frames of reference, because it's going to make all of this make a whole bunch more sense. Oops, not equals, minus. There's a minus sign here. Minus sign, that's important. So this is going to have it make a lot more sense after you watch this. So we'll end right here and come back to it, and I'll let you guys watch it. But the short answer is that let's say that I'm walking into frame right here. So if I'm walking here, I see, like, I'm walking like this. Well, actually, let me do it like this so my frame of reference is not flipped, because that's a mirror image. So right here, this is my right hand right here. And so I'm seeing, if I move this way, I'm seeing my computer move to my left, whereas the computer sees me move to their right. That's why there's this minus sign right here. Make sure that you don't have like a mirror image, because like when I look at the computer, it's all mirrored. This looks like my left hand, but to someone that's staring at me, like across from me, that looks like their right hand. Okay, we're gonna end right here though. We'll talk about this in more detail. Any quick questions before we go? So I'll post that video that I would like you to watch over the weekend. It's like a 20 minutes, and it'll help understand frames of reference a lot.
Thank you, Professor.
All right, you're welcome. Bye, everybody. Have a safe weekend.